Now let's detail the encryption mechanism, also known as ciphering, which ensures confidentiality for the transmitted data over the air. It is based on a symmetric algorithm using a secret key shared by the UE and the G node B. Let's detail a bit how it's done for the uplink communication from user equipment to the G node B. First, it is based on the XOR, exclusive OR, Boolean operator, bit per bit. Why? Because A XOR B prime equals A, if and only if B prime equals B. In other words, the plaintext A is retrieved by the G node B if and only if the algorithm computation done by the G node B is identical to the algorithm computation done by the UE. These computations are named the keystream block. Such a mechanism is very powerful because the keystream can be pre-computed even before the plaintext is available. This way, the plaintext can be ciphered very quickly using the simple XOR. The generic encryption algorithm for 5G is called NEA. More parameters than the secret key are used. What is important is that they cause the keystream for each message to be different, which is essential, because using the same keystream on different messages would make the mechanism much weaker and could facilitate successful cryptanalysis by the attacker. Third point, 3 specified algorithms can be used for NEA at the choice of the operator, and a 4th value for null ciphering algorithm is also available, making this encryption mechanism only optional. Finally, the secret key used for this algorithm is one of the keys shown in the comprehensive hierarchy previously, shared by the mobile equipment and the base station. In case of new radio G node B for the user plane encryption, that's the KUP enc. One risk with encryption is the known plain text attack. If an attacker can correctly guess some part of a plain text, the attacker will be able to change it in a specific way. With encrypted voice, it is quite hard for an attacker to guess anything. But this is not the case with protocol messages. When a UE connects to the network, one of the first messages in a user session may be a domain name service, DNS request, to resolve a name and obtain an IP address. The attacker may know which DNS service the UE is using. This helps the attacker to decode the IP address that is used in the DNS request. So the known plaintext includes the IP address. Using the ciphertext, the respective keystream can be extracted. This can then be used to encrypt the altered plaintext, such as the IP address of a malicious DNS server, to have the UE use an incorrect web page. The new ciphertext with altered plaintext is passed to the victim. The attack is then successful because the victim retrieves the altered plaintext instead of the original plaintext block. To prevent the known plaintext attack, integrity protection is used in addition to encryption. 3GPP introduced integrity protection even for 3G, but it did so for the control plane, not for user traffic. Some possible reasons were there is much more user traffic than control traffic, so introducing integrity protection would add considerably to the effort on the UE and the base station. The main service was voice. A bit error in a voice packet is completely harmless. Discarding voice packets with bit errors due to failing integrity protection or having to repeat them impacts the voice quality. In encrypted voice, a plain text attack is rather unlikely. This was not changed in LTE, although it was specified 10 years later. "5G introduces an optional integrity protection for the user plane to ensure that the data you transmit is not tampered with. Note, that integrity protection has been mandatory for the control plane since 3G. On the sender side, for example, in the user equipment, if we use the same example previously discussed, the integrity key is used. NIA is the integrity algorithm for 5G, and it is applied with the 3 available options. A message authentication code is then determined and sent over the air. Based on the hashing mechanism, it is 32 bits long, computed from the message, and a shared key of 128 bits. On the receiving side, the same key and algorithm are used to compute the expected message authentication code, or XMAC. If this is the same as the MAC, we are sure that there has been no change in the message. At the same time providing message origin authentication, i.e., the receiver has a proof that the message was computed by an entity knowing the shared key. Finally, we can note that the key used is different from the one used for encryption. In the case of new radio 5G access, for the user plane, that's KUP int. Let's finish this module with some quick knowledge checks. More than one statement may be correct, so select all that apply. Let's try one more question before we move on. Is this statement true or false?